So folks, in this first part of the video, we're going to continue our work on the Laplace transforms. And the first thing I want to do is, using the definition of the Laplace transform, we want to show that the Laplace transform of sine of at is a divided by s squared plus a squared, for specifically s greater than 0. So I'm not going to work through this one in the video. Instead, I've hyperlinked notes of me working through it. Just as a reminder though, while you may not be sure of exactly what steps to take, if you're asked to compute the Laplace transform of the sine of at, you should feel comfortable with the first step, which is to write this as the indefinite integral, or the improper integral from 0 to infinity of the sine of at times e to the minus st dt, and then go ahead and start working through this as best you can with the notes to help you when you get stuck, if you get stuck. The thing to remember with a problem like this, you saw this in Calculus 2, where you're going to perform the procedure of integration by parts twice, and then you're going to have to solve an equation for the integral that you're trying to obtain. And that's a little bit challenging. Okay, so pause the video and copy that over. It's a pretty lengthy problem, but do let me know if you have any questions on it. So now that we've got that, we'll just take this as a fact that the Laplace transform of the cosine of at is given by this expression here for s greater than 0. For those of you that are interested, I think there's a much more elegant way to derive both of these. However, it's also important that you review integration by parts. So I've opted to make sure that you review integration by parts. However, if you're interested, please take a look at this video. It's about 8 minutes long, and it's a chance to see a faster, kind of more elegant derivation for both of these Laplace transforms, given that you know the Laplace transform of the exponential function. So now that we've got the Laplace transform of each of those, we know how to compute the Laplace transform of the sine of at and the cosine of at, as well as the Laplace transform of e to the at. Let's go ahead and do this problem here. So here we're asked to use the linearity of the Laplace transform to find the Laplace transform of this function here, 5 cosine of t minus 2 sine of 4t plus 3 e to the 2t. And I'm going to be a little pedantic this first time through. So the Laplace transform is linear, so we can distribute the Laplace transform to each of these three terms. So this is equal to the Laplace transform of 5 cosine t minus plus the Laplace transform of negative 2 sine of 4t plus the Laplace transform of 3e to the 2t. Okay. Now usually we wouldn't pause and write this intermediate step, but I wanted to emphasize the linearity of the Laplace transform, and the first property of linearity says that we can distribute the Laplace transform over sums and differences, or that is, we can distribute the Laplace transform across terms. Now I can go ahead and, continuing to use the linearity of the Laplace transform, I can go ahead and factor out the scalars. So I can rewrite this as 5 times the Laplace transform of the cosine of t minus 2 times the Laplace transform of the sine of 4t plus 3 times the Laplace transform of e to the 2t, and we're well on our way. Now we just need to remember the rules, and each one of these rules we've either been given or derived. And so I know that this will be 5 times s over s squared plus, and I'll go ahead and write 1 squared there, which I could simplify as 1. There I'm using this fact from the previous page that the Laplace transform of the cosine of at is s over s squared plus a squared. This makes the assumption here, we should keep track of our assumptions, that s is greater than 0. We'll need that. Minus, and then we'll use the Laplace transform for the sine of 4t, which you've just learned. And this is going to be 4 all over s squared plus 16. Remember, that's using the derivation that you've worked for the Laplace transform of sine of at. Following the components, there's a. In the denominator, we have s squared plus a squared. And again, this one assumes that s is greater than 0. We need to keep track of these in case these aren't all the same domains for s. We need to take the most restrictive domain. Finally, the Laplace transform of e to the 2t we have is 1 over s minus 2, and this requires that s be greater than 2. And so all of this holds for s greater than 2. We'll have convergence of these integrals. So folks, we could clean this up. Let's go ahead and do so. We could write this as 5s over s squared plus 1 minus 8 over s squared plus 16 plus 3 over s minus 2. All right. Now I'd like to practice working backwards with the Laplace transforms using the inverse transform. And these are going to steadily get a little more difficult as we go along. Let's remind ourselves of a couple of facts. The first fact, and these would be obtained from a table. The first fact is that the Laplace transform of just a constant is that constant over s. Okay. More specifically, if we did the Laplace transform of 1, the Laplace transform of 1, and we derived this in class, is 1 over s. Then we showed that the Laplace transform of t was 1 over s squared. And in general, although we haven't proven this, the Laplace transform of t to the n is equal to n factorial all over s to the n plus 1. And this holds for n a natural number, and we should add for s greater than 0. Okay. Those rules, coupled with the rules that we've looked at today, should enable us to find all of these inverse transforms. So here we're going to be finding the Laplace transform, the inverse transform of 120 over s to the 6th plus 48 over s to the 4th plus 2 over s cubed plus 7 over s. And a few of these are going to be straightforward, and a few of them are going to be a little more difficult. In this case, I'm thinking about ways I could rewrite things, and remembering that I can distribute the Laplace transform, the inverse transform, through linearity, the same way I can distribute the other direction, the Laplace transform, through linearity. I can rewrite this as, I'm going to write it as 5 factorial all over s to the 6th. And here you can see that as we go further along, we're going to be able to say, using this rule right here, that this is the Laplace transform of t to the 5th. Let me say that again. The Laplace transform of t to the 5th is 5 factorial over s to the 6th. So the inverse transform of 5 factorial over s to the 6th will be t to the 5th. Now, in looking how this first term worked out, you might be thinking that we're looking for ways of writing factorials. And while that's partially true, the thing that we should focus on is the power of s in the denominator. So I'm thinking that this should look like the Laplace transform of t cubed. That's how we ended up with an s to the 4th there. So I think I should have an s to the 4th inside this transform. But then for me to be able to apply the inverse transform, I need this to be 4 minus 1, or 3 factorial. 3 factorial is 6, so I'll put a 6 here, and so that should be 8. Notice that if I were to distribute this 8 back into the Laplace transform, I'd have 8 times 6, which is the original 48 that I have. But now, it's possible for me to see that this will be 8, and this is the Laplace transform. The 6 over s to the 4th is the Laplace transform of t cubed. So we end up with t cubed there. Again, folks, if working backwards with the Laplace transform is difficult, and I think it is, it's always easier to check your work. If you were to take the Laplace transform of 8 times t cubed, it'd be 8 times, and then we would have s to the 4th underneath 3 factorial. So that checks. This next one looks to me to be all ready to go. This would be just the inverse transform of 2 over s cubed, and that'll work out nicely because that's just the Laplace transform of t squared. This last one, plus, and here I'm going to write it as the 7 times the Laplace transform of 1 over s. 1 over s is the Laplace transform of 1, so we'd have plus 7 times 1 when we do the inverse transform. So this whole thing cleans up to be t to the 5th plus 8t cubed plus t squared plus 7. In my opinion, the hardest of these was this one right here. And remember, the key was to focus on the power and not the coefficients. So if this is s to the 4th, I'm trying to build, using this rule right here, I'm trying to build something that looks like n factorial over s to the n plus 1. So if this is s to the fourth, n in this case will be 3. And so I ensured that I had a 3 factorial in the numerator. And I got there by factoring an 8 out of the denominator. Okay, so let's practice this last one. In this case, we're asked to find the inverse transform of these functions here. That's an s. Let me fix that. S squared plus 7 plus 4 over 5s plus 2 plus negative 2s plus 6 all over s squared plus 4. Now, in general, while taking the Laplace transform is a messy calculation, it's always the same calculation that we're doing. It's pretty rote. When you're trying to find the inverse transform, you're often trying to be creative, to think about the rules that you know, and to write this in terms of the rules that you know. So I'm looking at this first term here that I want to take the inverse transform of. And to me, this looks structurally fairly similar to the Laplace transform of sine. Remember that the Laplace transform of sine of at through the work that you've just done is a over s squared plus a squared. So it seems to me that a would be the square root of 7. But I don't have the square root of 7 up here, so it's not a perfect transform. So what I'm going to do is I'm going to go ahead and rewrite this as 1 over, well, let me do this in 2 steps. I'll write it first as the square root of 7 over the square root of 7 times the Laplace transform of 1 over s squared plus 7. And I'm in the process of distributing the Laplace transform to each of these 3 terms. But then, because I want this to be the this to be the result of having done the Laplace transform of the sine of at, I need to do some rearranging. So I'm going to leave this square root of 7 in the denominator outside the transform and move the scalar in the numerator inside the transform. And so we end up with this expression here. Now this is the Laplace transform of the sine of the square root of 7, t. So this comes out as 1 over the square root of 7 times the sine of the square root of 7, t. And in general, folks, as I've said before, I think this procedure is pretty difficult. It's a lot easier to apply the Laplace transform to this result and see that you can get back to the original expression there. All of this has just been doing the Laplace transform of the first term. We need to take the inverse transform now of 4 over 5s plus 2. What I'm going to do here is I'm going to rewrite this. I'm going to go ahead and factor out, first of all, I'll factor out a 5 from this. When I do so, I'll have 1/5 times the inverse transform of 4 all over s plus 2 over 5. And I could have done this in one step, but you'll see that I'm on my way to building the result of having done the Laplace transform of an exponential function. Again, just as a reminder, if we take the Laplace transform of e to the at, that's equal to 1 over s minus a. So if I see something that looks like, specifically noticing the power here, this is s squared, but this is s to the first power, I'm trying to build something that looks like 1 over s minus a. So the first thing I did was I divided the 5 out of this denominator here so that the leading term was just s. The result was then we have the 1/5 that we divided out times, and then in the denominator we have s plus 2 divided by 5. Okay, the other thing I can do is now pull out that constant, and I could have done that in the first step. So this gives me 4/5. Careful, my s's might look like 5s. Be a little more careful here. 4/5 times the inverse transform of 1 over s plus 2/5. Now, what I have inside the inverse transform looks very much like the result of having done the Laplace transform of e to the at. So we end up with plus 4/5, and then we have e to the, careful, watch your sign, minus 2/5 t. There. And I'm out of room here, folks. I apologize for that. Let me finish this out, and I'll give you more room in your handout. Let me just pull this over here. So the last term that I need to take the inverse transform of is this term right here. And you can see it's almost ready to, it's not ready to go, but I can kind of look ahead and see that I'm expecting to get a cosine and a sine out of it. I'm going to rewrite this as the inverse transform first of negative 2s over s squared plus 4 plus the inverse transform of 6 over s squared plus 4. Now we're not there yet, but we're on our way. I can see that I'm trying to build this to look like the result of having done the Laplace transform to a cosine function. So I'll factor out the negative 2 inverse transform of just s over s squared plus 4. Then I can go ahead and conclude that that term will be minus 2 times the cosine. Careful, remember that's a squared, so that's 2t there. For this one, I'm in the process of making it into the result of having done the Laplace transform of a sine function. So in this case, I need it to look like a over s squared plus a squared. So a is going to be 2, so I'll factor out a 3. Then I end up with the inverse transform of 2 over s squared plus 4. Folks, if ever I do a move that you don't understand, go ahead and do the opposite direction of that move and confirm that you get the line above it. So then I can say that this is equal to the inverse transform of this term will give me 3, and then that's the sine of 2t. And here I've given the inverse transform for this large expression here. So folks, we'll pick this up in the next video, but the next one incorporates a very special technique that we will do a couple of times in this class, so I want to make sure we go slowly through it. If you want, give it a shot on your own, but I'll pick that up in the next video where we give that, where we give the inverse transform of this quadratic right here. I'll see you in the next video.